start today our series of plasma physics for the subject of reactive media, which is separated into plasma physics and combustion. Okay, so plasma is an ionized gas. I think you guys know that. So to talk about plasma physics, it's really important we start with introduction to collision phenomena, right? So we have two types of collision, elastic and inelastic. Okay. Momentum is conserved in either collision. Generally, what changes is the conservation of kinetic energy. Energy is conserved, but kinetic energy might not be conserved. For elastic collisions, it is conserved. So you have a particle with a certain kinetic energy. Before and after the collision, it's going to be the same. And for inelastic collision, it's not. So the velocity will change, and energy cannot be destroyed, so the energy that is not conserved from the kinetic energy must go elsewhere. And where it goes depends on what type of inelastic collision you have. You can have excitation, dissociation, ionization, dissociative attachment, many more. So the kinetic energy is transformed into something else, potential energy, whatever. And since we have so many different types of inelastic collisions, it is important to define another variable, quantity, that defines that characterizes a collision, which we're going to say the cross-section sigma. And this number varies. We have multiple sigmas, one for each type of collision, with that being, of course, the area that is the effective area for that type of collision. So, for example, I have a particle here moving, and we have this cross-section here. That means that if another particle gets within this cross-section, it characterizes as an interaction is going to occur. Something's going to happen, right? This area over here is what defines when something's going to happen. If a particle enters this area, that means that it will characterize a collision. Okay, collision and interaction, right? So we have sigma that is dependent on the kinetic energy, okay? Okay. All right. So let's start from here. We have a plasma in here. Okay. So we're gonna get a plasma cross section in here, full of target particles, right? Absolutely full of target particles. And we have a beam of projectiles. Oh God, a beam of projectiles that will pass through this infinitesimally small volume. Okay, I'm gonna call this dx. I'm gonna call the number of particles here np, and this one for projectile, and np for end target. Okay, with a flux gamma and an area here I'm gonna call a. Okay, so we can see that the change in the beam density of particles, will be equal to minus np nt sigma dx, and this is acceptable. You can take this. The change in density of change in density of particles in the beam, incident beam, is equal to minus because the characteristic collision is decreasing the number of particles, is proportional to the number of particles you have in the beam, the number of particles you have in the plasma volume target, whatever, times the cross section, which we discussed before, and dx. Okay, so we can say that we can also call this the flux gamma that I talked about before. This would be just minus gamma 0 nt sigma dx. We can do some manipulations in here and integrate this equation, which will give us that sigma of x should be equal to sigma 0, right? Sigma 0 that multiplies 1 minus e to the power of minus x over lambda. And lambda is the free mean path, which is to say the average distance a particle moves without a collision. And it's just a simplification. If you integrate this equation above, you'll see that lambda is nothing more than nt times sigma. Okay, this is an important parameter here we will be discussing. Okay, so with that out of the way, we can define something called a rate constant. Okay, so in our original equation we have that. Oh yeah, also something else that it's important. We have dnp equals to minus np nt sigma times dx, right? Sigma dx. We can also define dx as being v dt, and by rearranging this we have that dnp dt equals to minus np nt sigma v. Okay, and from this definition we can propose something called the rate constant. Okay, which is to say, this I'm going to call a rate constant, and therefore our the speed at which the density in the beam changes is going to be equal to, or in other words, the collision frequency. The collision frequency would just be dnp dt 1 over np equals to minus n t sigma epsilon v. Yeah, or we can just simply say that this is equal to our rate constant k. So this would be this I'm going to call mu equals to minus ntk. Okay, so yeah, I think that's it for these definitions. However, the rate constant is really important, and this calculation that I made here is assuming various simplifications, spherical hard spheres, etc. So it's not really practical. We also assume here that the cross section is constant, which is not true. I even wrote it here as being dependent on the kinetic energy. Therefore, we have a better way, a more elegant way, if you will, to define the rate constant. So for a plasma in thermal equilibrium, we have that the fraction of particles that have velocity between v and dv, v plus dv, is given by the Maxwell-Boltzmann distribution. And therefore, if we want a more, let's say, realistic rate constant, we can say that this is the particles. This is a distribution, right? So fraction of particles with velocity between Jesus Christ between v and v plus dv is fv, which is a function of v, should be equal to m over 2 pi kbt 3 to exponential of minus mv squared 2 kT, where Kb is a constant, T is the temperature, and M is the reduced mass of the system. However, when we're dealing with electrons and with electrons and heavier particles, the reduced mass of the system can be simplified. Okay, and we also have the fraction. Another important distribution is the fraction of particles with a velocity modulus between v and v plus dv. So this is the modulus. Okay, so this is again a function of v, 4 pi v squared that multiplies m over 2 pi kbt over 3 over 2 exponential of minus m v squared over 2 kt. Now we have more or less a distribution of velocities, because in a plasma we don't have like all particles moving with the same velocity all the time. So to find the rate constant, we need a way to take that into consideration, right? So the new rate constant, which is equal to the cross-section and the relative velocity between AB, is equal to the integral of this function over here, the one I'm using W because the books use W, but I think W is a little weird, is equal to VAB, which is this function over here, times sigma, which is the cross-section, W, Jesus again with the W, VAB dVAB. Okay, so now we have a way to calculate the rate constant, and I think that's about it. This is the first video. I think covered everything. Now we can start doing the TD. I'm gonna try to solve it, but basically this is just to get familiar with some important parameters in plasma physics. So collision, rate constant, fluxes, freeing path. There's the Debye length as well, which I haven't talked about. It was basically the length in which if you insert an electric charge in the plasma, the effects, what is the distance in which the effect of the electrical field induced by the electrical charge is important. So it has an effect on the plasma. Right, very important parameters. Yeah, I think that's about it.